Hello everyone and welcome back to a new video in our Autodesk Robot structural analysis tutorials. In this video we are going to go back to the basics and explain something called influence surfaces in Autodesk Robot. Now, influence surfaces and influence lines are things that you should have studied in structural analysis, especially influence lines. If you haven't done that before, I will link two videos on the top right. One of them explaining how robot performs influence lines, and the other one explaining what an influence surface is, which is part of a previous video. Anyway, let's jump into the topic, so sit back, relax, and enjoy the show. Alright, now before we start, I'm using Autodesk Robot 2024, and to be able to see influence surfaces, you will have to select Shell Design as your template. If you don't find Shell Design here, you can just click on New and select Shell Design from here. So now we are in Shell Design. Now, to explain the concept of influence surfaces, I'm going, of course, to model me a very simplified structure. So let's take a look on that. I'll select on the grid or axis definition. I'll define me in the X, 0, and 5. In the Y, I will define 0, 5, 10, and 15. And in the Z, I will define me as 0. I'll apply and close, and then click here for the isometric view. This is a very simple 3-span thing. Now here, I will click on members, and I will define me a reinforced concrete beam with a section of 300 by 500. I could make something bigger. For example, I could click here and define my section that is, for example, 400 by 800. So choose the section you want. I'll add that and close, and then I will just draw my 3 beams. I'll draw me a span from here to here, that's 1 span, and from here to here, that's the second span. Similarly, I will draw me here 1 span, and here another span. Maybe I should add a middle beam, so okay, let me go very quickly to my axis. To my X, I'll add a 2.5, I'll apply and close and draw my 3rd beam. Similarly, I'm drawing 1 span here and another span here. So those are my main beams. Now I'm gonna go select me 300 by 500, different section. So I will use it and draw me those secondary beams, if you want to call them. So there you go. Those are my beams now. This is just a dummy structure because I want to show something called influence surfaces. So I need some supports for this dummy structure. I will basically support me some pins here, and I'll apply me here 3 pins and here another 3 pins. So 2 lines of supports. Fantastic. Now on top of all that, I will go to my slab here or my structural elements. I select me here a floor, and I will select me a thickness here. Let's define a thickness. So here I will define me a thickness, calling it, I don't know, thickness 200 or something. 200 might be too small. Let me see, 5 by 100. 250 maybe, to make more sense. This is 250. I'm not reducing any inertias. I'm not changing any materials because that's not my point today. So I'll add that, close, and then define it. So I'll use rectangle. And notice I'm defining 1 full panel for the entire element. So 1 full panel. So what I'm saying is you have 1 plate that covers everything. So yeah, that's everything. We are ready to do our influence surfaces. Now I will remind you that it's very important for you to understand what an influence surface is. Let's start doing our influence surfaces. To access influence surfaces, you don't need to apply any loads. All you have to do is to go to Loads, Special Loads, and Load Pattern. This is only accessible if you are in the Shell Design system. That's why it was important to select the Shell Design template. When you click on Load Pattern, it asks you, where do you want the load to move? Because the influence line gives you the values at a specific point when the load is moving around. I will reuse footage of my previous explanation of influence surfaces from the previous video to kind of make sense. You can skip to the timestamp that is shown on the screen if you want to skip the theoretical explanation. Now, what is an influence surface? An influence surface is a generalization of an influence line. What is an influence line? Now, I know that you have studied this in structures, but let me give you a quick reminder. If you have a certain beam, let's say you have a simply supported beam with a ruler here and a pin here, okay? There is a major difference between the bending moment diagram and the influence line. So what does the bending moment diagram answer? What is the question that the bending moment diagram answers? The question that the bending moment diagram answers is, what is the bending moment at any point on the beam if the load is positioned at a certain point? This is what a bending moment diagram does. Basically, if you have a load, then of course we all know that the bending moment diagram for this thing looks like this. Of course, I'm drawing positive downwards, so I'm using the design bending moment diagram. You could draw positive upwards, not my point here. So what is the bending moment diagram? The bending moment diagram is the answer to the following question. What is the bending moment value at any point X for a fixed load? So the load is not moving, but the point X is moving. Let me explain this differently here. Let's say you take the bending moment diagram value here, and let's say the value is 5. This value 5 means that the bending moment value at this point for a given load is 5. Let's take another value. Let's say this one. And this value is 7. This means that the bending moment value at a point here, when the force is given, is 7. Notice that the point is moving and the load is not. That's why the bending moment diagram answers the question, what is the bending moment at any point on the beam if the load is at a certain position? Now, what is the influence line? I like to call it the inverse of a bending moment. Allow me to explain. And you have, for example, once again, a simply supported beam, and you want to know the influence line for the moment at this point. What you do is, of course, here I'm saying Müller-Breslau. It's a long story. You should learn this from structural analysis books. But according to Müller-Breslau's method of drawing an influence line, you would have to apply two moments like this and bend the beam like this. Of course, I'm going to use the design moments, so I'm going to bend it like this. Okay, now they look similar, it seems, because it's a simply supported beam, but there is a major difference here. The major difference is, first of all, we drew the influence line without knowing the force. We don't know what the force value is. The only thing we know is the force position. Okay, that's the first thing. Influence line is using a unit force to be drawn. Now, what does the influence line mean? To understand what an influence line means, I want to explain what the influence line answers. What is the bending moment at a specific point when the load is positioned at another point or at any point? You see how things changed. For the bending moment diagram, the point was any point, meaning the point was moving, and the load was specific, it wasn't moving. This is vice versa. If I say that this is the influence line of the moment at this point, let's read what the influence line tells us. If I read here and see, for example, here a point 2 as a result, what does this point 2 here mean? It means that if the force is placed here, the moment on my target point is point 2. It takes some time to get used to it, but that's how it's read. Let's take another point. Let's say that I want to measure what this point means. And let's say this point is 0.5. Of value. This is an influence line, ladies and gentlemen. For the 0.5 meaning here, it means that if you place the force here, then the moment on your target point is 0.5. Look at the difference. I will remind you of both readings. So this value and this value. I will compare how we read it. This value means that for a given force with a certain position that doesn't change, the moment on a point here is 7. However, for this point, how will I read it? This point reads as follows. For a specific point that never moves, when the force is positioned here, the value of the moment at that specific point is 0.5. I hope this makes sense. Now, if it still doesn't make sense, you might need to brush up your structure analysis skills, so check out a book by R.C. Hibla. It might be interesting. And this is an influence line. For the moment, of course. What is an influence surface? The influence surface is an extension of the influence line. When you study the influence line, you usually learn that you have a certain beam, standalone, disconnected from the entire world, and a load is moving on it. However, that's seldom the case. A beam is usually part of a big structure. Let's say we have one beam here and one beam here, just for simplicity's sake. And of course, those beams are connected by a slab. So there is a slab here between them. And of course, let's put some supports here. Everything is pinned. So this is pinned, that's pinned, and that one is pinned, but you cannot see the pin. Okay? Let me show you how an influence surface is drawn. Let's target this point and say that you want to have the influence surface of the moment at that point. You would have to take a point load with a value of 1 and move it everywhere on the entire surface. And on every place on the surface, you will have to get the moment value here and plot it. So it would look something like this. The further the load is away, the less effect on the moment it has, and almost zero here. Let me just try. I'm not really good at drawing 3D. Just gonna try draw this. Of course, this is just a quick drawing. You need to, of course, solve it step by step. I might make an Autodesk Robot video where I explain to you how those things mean and how you could actually verify them by hand. This is an influence surface. What does it say? Well, let's take a look on this point, for example, here, this point. This point might have a value of 0.2 or something. What does this point mean? This point means that if the one force is here, the moment on this point is 0.2. I hope it makes sense. Now, why do you need an influence surface? You need an influence surface because you want to know where to put your car, and where to put your pedestrians, and where to load your loads, the live loads especially. You need to place the loads in such a way that makes it as bad as possible on the beam, i.e., it increases the moments and shears to the max. That is the topic of today. I had to do this little theoretical dive here because influence line seems to be one of those topics that people tend to have problems with it, and this is influence surface, so it's an extension of what an influence line is. Anyway, the panel I want to apply an influence surface for is panel number, I don't know, number 3 or something, 14 it seems. So I want to add influence surfaces. Now let me remind you that there are members. We have drawn some members, and those have numbers. For example, this beam here is member number 4. That beam here is member number 5. 8, 9, 6, 7. Those numbers will become important very soon. Also, nodes have numbers. If you click on this point, you will see the node numbers. 6, 12, 9, 5, 16, 7, 13, 10, and so on. Because when you want to apply an influence surface, you need to tell him where the point is that you are applying an influence surface for. If you click on Add, you can apply influence surfaces for points, for plates, and for beams. The default option NTM is for beams. So let's talk about member number 8. And I want to know the moments and the forces, shear, axial, and so on, at a point, let's say here, near the center, so around 0.4-ish. So how do I do that? Well, my element that I want is element number 8, that's a bar. The position of the point is 0.4 from the start of my drawing. If you forgot how you drew it, you can click on the local system and it will tell you exactly how I've drawn it. You have drawn it from here 12 to here 13. You can see this by the local x-axis. So 0.4 is measured relatively from 12 to somewhere here. And what do you want to see at this point? My target is around this point. What do I want to see for this point? Let's say I want to see moment x, which is torsion, by the way, and I'll add that. And you can notice that there is a mx added. Then I will see my, which is the bending moment around the y-axis. I will add that. mz, I will add that. mz is a somehow bending moment, but from wind loads, for example. Then I want to see the axial compression and tension, the shear in the y, and the shear in the z. Now, to be honest, the most important values are going to be the moment around y and the force around z, because the moment around y is the typical bending moment, and the force around z is the typical shear force. That's not everything. I also want to talk about node number 12. There are reactions at node number 12, and I can draw influence lines for their actions. I keep saying influence lines, but what I mean is influence surfaces. How do I do that? Well, I'll add again, and this time I'll go to node, and my target node is 12. The numbers are important here. And of course, you can apply reactions and so on. So I will see, I don't need the displacements because this is supported. We know that this is going to have 0 displacements. If you want something that has displacements, you could select something that's unsupported, like 15. But since it's supported, I want to see the reactions. Just let's put FZ here, just for the sake of experimentation. And there we go. There is one last thing in detailed, which shows you the influence surface for the internal forces of a slab element. You might be tricked into thinking, my panel number is 14, so I should put element 14. The answer might surprise you. I'll put the element 14 here, and hoping that it will work. And I will just start showing, for example, moment in the x, moment in the y, shear in the x, apply, and shear in the y. apply. So you think, okay, 14, because my panel number is 14, you will be surprised very soon. We're finished basically. So I'll close this, and now we are ready to let the magic work. I will generate, after making sure that panel 14 is selected, because that's panel number 14. If you click on generate, the robot will start calculating stuff. So I click on generate and wait a little bit, and the robot is doing its magic at the moment. And there we go. Calculations are completed. For visibility's sake, I will remove the local axis here. I will remove the bar numbers, and I will remove the node numbers. Now you can see the influence surfaces. For example, if you click here and click apply, nothing happens, it seems. Well, nothing happens because you did not select what you want to see. So you could select positive and negative and click OK, and it seems something is happening, but it's kind of clipping in and out of reality. This is a mistake done by the developers, and I know exactly programmatically why it's happening. If you are a programming nerd like me, it's because they are using OpenGL and they have two surfaces that have the same z-axis, so the OpenGL freaks out and doesn't know exactly what to render. I'm going to fix this issue by telling it not to render the panels. So if you click on that, you remove the panels and you can see the influence surfaces perfectly. See, now my programming skills are helping me. Now what is this? This is the influence surface of the MX of element number 8 at point 4. Let me remind you, this is element number 8, this beam is element number 8, okay? And we are talking about the torsional moment at 0.4 of its length. And that's why you can see that this point seems to be very critical. This point is actually 0.4 of its length. So tools, dimension lines, let me show you from here to here. That is 3 meters. And the element is, I think, 8 meters long. Is it 8 meters long or 10? 10, yeah. So it's around 0.4, not perfectly 0.4. The reason why it's around 0.4, because due to the finite element mesh, that's the closest it can get to. It's not perfect, but it's something, I suppose. So this is the torsional influence surface of the torsion at this point. These are given in contour maps. So what does 0.75 negative mean? 0.75 negative means if you put a force anywhere on the line, if you put a unit force down any place on this line, then the torsion at that point is going to be 0.75. What does, for example, negative 0.25 mean? Negative 0.25 means if you put a force on any point on this line, on this contour line, then the torsion on this moment, on this point, is going to be 0.25, and so on. Now, torsion is okay, but let's take a look on the MY, which is the more interesting one. So I click on MY and hit apply again, and this is really beautiful. This makes perfect sense. Because remember, look at the supports. You have 3 supports here. You have a support line here and a support line here. So it looks like a cantilever beam, but of course with a slab now. Remember, our target point is somewhere here. So you can see that if you apply a force exactly on your target point, then you will get the maximum positive moments. If you apply a force on the cantilever, you will get a negative moment here. I mean, this is from structures, right? Let's make a simplification. You have a beam like this that is kind of extending or overhanging. So you have a support here and a support here. And you are interested in the moment on this point. The influence line of this moment on this point looks kind of like this. Using Müller-Breslau's principle, it looks kind of like this. That's the influence line on the moment of this point. Now, influence surfaces are 3D of the influence line, but you can see that on the overhang, you will have a negative effect of moment on this point, and inside the span, you have positive moment effects. So you can actually see this perfectly fine here. Any load applied on this position will give you a negative moment here. Any load applied on this position will give you a positive moment here. For example, if you put a force here on this contour line, the moment on your target point is going to be negative 0.5. Let's go to MZ. I think it will be 0 because there is nothing. Yeah, it's fully 0. Because no gravity load will cause moment around Z. Fx, that's the compression tension. I think it will be 0. Yeah, same thing. Fy is 0. Fz is not 0. Fz is the shear. And you can see once again the influence line in action. This is a surface, but if you want to go back to your 2D element, if you want to do the influence line for the shear, I think what you have to do is to apply a shear like this, and one part will go up and one part will go down on something. I think I messed up my directions. I think it should be down and up. But my point still stands. This and this have the same effect. This has an opposite effect. If you look here, you can see this and this have the same effect, and that one has the opposite effect. Pretty cool. What about reactions? Well, if you go to FZ and apply, you can see that the reaction will increase the more the force gets closer to the reaction. For example, if the force is exactly above the reaction, the influence value is 1. The further the force goes away, the less the reaction will be. For example, if you put a force on any point on this contour line, then the reaction at this point is half. And so on. You can even see that the influence line here is negative, or surface. This once again makes sense because in our 2D problem, if you want to draw the influence line of a reaction, you have to push this up, and that's your influence line using Müller-Breslau theory, which is well reflected here. If you want to see mxx in 14, this is where things are different. You thought mxx for 14 is mxx for the entire slab. That is not the case. If you click mxx on 40, you can see that it seems that, and by the way, mxx is the moment on the slab element in the direction x. Check out my slab videos for that. I will link it top right. But it seems that the center of this entire thing is here. So it seems that this element is what is mxx being calculated for. And this can be further verified by checking myy and checking qxx and checking qyy. So it seems that this element is the center of our investigation. But why? Didn't we click on element 14? And if you click on the number here for the panels, it is indeed panel number 14. So what gives? Well, the problem here is that you misunderstood what robot means. When it asks you for the element of the slab, it doesn't ask you for the serial number of the slab, but it asks you for the serial number of the finite element inside the slab. This might be strange for you, but you see those little rectangles? Each one of those rectangles, or parallelograms, each one of those elements, for example this one, each one of those elements has a serial number of its own. And it turns out that this element has a serial number of 14. And the question becomes, okay, how can I see the serial number? Well, you will have to right-click here, click on Display, and then go to something called Panel FE, and there is something called Finite Elements here. If you click on plus, there is something called Finite Element Numbers. If you enable this and click on Apply, then you can see the numbers of each one of the finite elements of the slab, and lo and behold, element 14 is here. So now the question becomes, okay, how did you know that element? Like in the beginning, you don't know what the elements are. Like before you do your analysis, you don't know what 14 is. How did you predict that? You could predict this by first of all meshing, and then after the fact, looking where the element is that you want, and then applying the load pattern for it. To my final point in this video, why do I even need influence surfaces? You need influence surfaces, especially if you have moving loads, because you could place the moving load in such a way to maximize the effect of the moving load on, for example, moment. By placing the moving load or the distributed load on the green area, you are maximizing the negative moment or positive on the element. And by putting it on the red place, you're maximizing the opposite. This is what Autodesk structural bridge design software does, and that was the topic of my previous video on that software. Take a look on that if you want to see more details. So yeah, that's everything what I wanted to talk about today. I wanted to cover something called influence surfaces. I hope you enjoyed. Of course, if you have questions, please feel free to leave them in the comment section. And before I finish, I want to give a influence surface size shout out to my dear channel members in the contributor level and the helper level whose names are going to be shown on the screen. I want to thank them from the bottom of my heart, as the support of the channel is priceless to me and enables me to provide you with videos hopefully on time and with a certain quality I try to achieve, and for that I am forever thankful. In the end, I hope that you enjoyed the video and you found it beneficial. If you have enjoyed the video, then please consider liking, sharing, subscribing, commenting and so on, especially subscribing because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel, and we'll catch you in the next video. Bye bye.